Okay, let's dive into this. Welcome to The Explainer. Today, we are setting out to map the intricate and honestly sometimes terrifying ways that toxidromes, which are essentially toxic syndromes or constellations of clinical signs, exert their systemic effects all across the human body. We're going to look at exactly how foreign substances, or xenobiotics, completely compromise our most vital systems, and how medical science fights back. So, what actually happens when a tiny, microscopic toxin completely rewires your body? It's a fascinating but really sobering question. We usually think of trauma as this huge, macro-level event, right? Something we can easily see. But poisoning is a microscopic trauma. It's this silent invasion where tiny molecules cascade through your bloodstream, flipping biological switches, disabling alarms, and ultimately leading to total systemic failure if it's left unchecked. Just to put the real-world stakes into perspective for a second, think about this number. According to the American Heart Association, in just a single 12-month period ending in April 2021, over 100,000 people in the United States died from poisoning and drug overdoses. It's a staggering loss of life, and it really underscores why understanding the mechanics of toxicity and the rapid interventions required to reverse it is an absolutely crucial necessity in modern medicine.
Let's move to our roadmap and see how this builds. We've got 4 distinct chapters today. 1. Systemic overload. 2. Central command crisis. 3. Sensory sabotage. And 4. Critical resuscitation and antidotes.
Starting with Chapter 1, Systemic Overload. This is all about hijacking the body's global thermostats and fluid balances.
Now, before we look at the disruption, we really have to understand the baseline. Think of thermoregulation as your body's ultimate climate control. It's a complex physiological process run by the anterior hypothalamus, and it maintains our core temperature at a super tight set point of 98.6 degrees Fahrenheit or 37 degrees Celsius. It is a delicate balancing act of heat production and heat dissipation. When a poison enters the system, it can drastically alter the set point, leading to life-threatening hyperthermia or hypothermia.
When it comes to dangerous hyperthermia, there are basically 2 main ways a toxin can completely mess up this system. On one hand, you have drugs that just massively crank up your endogenous heat production. These are things like cellular uncouplers. They essentially bypass your body's normal energy controls and throw your metabolic furnace into an uncontrolled overdrive. On the flip side, you have drugs that impair heat dissipation, like anticholinergics. These drugs actually inhibit diaphoresis, which means they physically stop you from sweating. This often presents with really distinct dermatologic signs. Think red, hot, dry skin. So while one toxin overworks the furnace, the other completely shuts down your built-in cooling system, and both pathways lead to the exact same dangerous overheating.
So the absolutely crucial point here is that poisoning doesn't just wreck your temperature. It totally devastates your fluid and electrolyte balances system-wide. A patient might experience severe volume depletion through intense gastrointestinal losses, or severe hepatic distress as the liver desperately tries to metabolize the threat. The renal and genital urinary systems take a massive hit too. Toxins can cause renal tubular acidosis, severely impairing the body's ability to balance acids. Or consider ethylene glycol, which is found in antifreeze. As your body metabolizes it, it creates calcium oxalate crystals that physically precipitate in the renal tubules. It's like microscopic glass, leading to acute kidney injury and rapid metabolic failure.
Moving to Chapter 2, Central Command Crisis, the toxic disruption of the brain and behavior.
All right, so what's happening up in the brain? Toxins cause neurotoxicity by literally sabotaging your normal neurotransmission. And they generally do this in one of 2 ways. Some xenobiotics directly interact with receptors. Cocaine, for example, enhances neurotransmission by directly stimulating specific pathways. Alternatively, you have drugs like amphetamines that act almost like biological hackers. They are taken up into the cell using your own existing catecholamine transporters, and once they're inside, they force the neurons to uncontrollably dump their chemical stores. It is literally microscopic sabotage of our central wiring.
And this brilliantly illustrates how medical professionals actually measure that exact sabotage. When a patient's central command is heavily suppressed or excessively agitated, clinicians can't just guess the severity. They rely on validated scoring systems mapped out on tools like receiver operating characteristic curves, specifically for things like the Richmond Agitation Sedation Scale, to accurately quantify the depth of a patient's altered consciousness. This scoring is absolutely vital because it directly predicts the need for critical interventions, like inserting a breathing tube.
But here's a wild concept. This disruption isn't always about the presence of a toxin. Sometimes it's about the sudden absence of one. Chronic alcohol use fundamentally changes the brain's receptors over time. So when alcohol is abruptly removed during withdrawal, the brain experiences this intense neurochemical whiplash. The patient suffers a sudden decrease in GABA, which is the brain's primary inhibitory signal, and a simultaneous increase in glutamate, the primary excitatory signal. This perfect, violent collision of lost inhibition and unchecked excitation is exactly what causes severe psychomotor agitation and dangerous autonomic excitability.
Chapter 3, Sensory Sabotage. Poisons entering the specialized organs of sight and sound.
Now, what's really interesting about this next concept is how sneaky it is. When it comes to ocular exposure, we have to talk about the Trojan horse concept. If a toxin gets into the eye, it doesn't just stay in the eye. Through the conjunctival capillaries and nasolacrimal drainage, up to 80% of an instilled drug can be absorbed directly into the systemic circulation. And because it absorbs this way, it completely bypasses the liver's first-pass metabolic removal. The toxin literally sneaks past our primary filtration organ and goes straight into the bloodstream.
Because this systemic absorption happens so incredibly fast, mechanical decontamination has to be immediate. Literally every single second counts. The critical protocol involves immediately retracting the eyelids, applying a local anesthetic so the patient can even tolerate the procedure, and continuously irrigating the eye with fluid for no less than 10 to 20 minutes. Only after this mechanical flushing of the Trojan horse is fully complete do we move on to checking visual acuity and performing a detailed slit lamp examination to assess the structural damage.
And you know, our ears are just as vulnerable, which is a condition known as ototoxicity. It's actually kind of wild how many surprisingly common medications, stuff you might even have in your medicine cabinet, can damage your hearing. Reversible hearing loss, or tinnitus, which is that persistent ringing in the ears, can be caused by salicylates, NSAIDs, and loop diuretics, but it gets worse. Drugs like aminoglycoside antibiotics, chemotherapeutics like cisplatin, and heavy metals cause irreversible damage. They trigger cell death in the delicate outer hair cells of the cochlea, leading to permanent deafness.
We rely so heavily on our senses to warn us of danger, right? But our biology has some seriously surprising blind spots. Take our sense of smell, for instance. You've probably heard that deadly cyanide gas smells like bitter almonds. But here's a truly alarming statistic. 40 to 45% of the human population has specific osnomia for that exact scent. It is a genetic inability to detect it. This means that for nearly half of us, our natural biological alarm system is completely, terrifyingly flawed against a lethal, fast-acting exposure.
Finally, Chapter 4, Critical Resuscitation and Antidotes. Rapid system overrides when basic resuscitation just isn't enough.
Managing a critically poisoned patient is essentially a dual-track process. On one side, standard resuscitation absolutely always comes first, securing the airway for respiratory support, managing breathing, and stabilizing the cardiovascular system to maintain hemodynamics. You have to keep the patient alive. But on the other side, we have antidotal therapy. A patient poisoned by certain cardiovascular drugs might not respond to standard vasopressors or CPR at all. To actually disarm the microscopic threat, providers must administer targeted molecular antidotes that reverse or bypass the poison at its specific cellular target.
Consider this your master key. It's basically a microscopic battle plan. These are the specific antidotes recommended by the American Heart Association to physically fight off toxins for control of the body's receptors. For opioid respiratory depression, we use naloxone. For severe benzodiazepine toxicity, it's flumazenol. If that invisible cyanide strikes, hydroxycobalamin steps in to restore cellular energy. For beta-blocker overdoses that are completely crashing the heart, we actually use high-dose insulin to bypass the blocked receptors. And for life-threatening local anesthetic toxicity, providers administer intravenous lipid emulsion, physically pulling the toxin away from cardiac tissues. It's amazing stuff.
But what happens when the poison is just so overwhelming that the heart and lungs completely fail and those antidotes aren't working fast enough? Well, enter the ultimate mechanical override, VA-ECMO, or veno-arterial extracorporeal membrane oxygenation. This highly advanced life support machine literally pumps and oxygenates the patient's blood outside of their body. It acts as a vital mechanical bridge to survival. It keeps the patient's tissues alive just long enough for their own hematologic system, their liver and their kidneys, to natively clear the poison from their body.
Which leaves us with this final, really provocative question to ponder. As synthetic toxins and pharmaceuticals constantly evolve, becoming more complex and far more potent, where does our ultimate defense lie?
Is it in an endless race to engineer new molecular antidotes? Or does it lie in a much deeper, fundamental understanding of the delicate, interconnected machinery of the human body that we just explored? Thank you so much for joining me on this systems check, and keep asking the right questions.